heat transfer by conduction. And our basis here is Fourier's law. Okay, so according to Fourier, the rate of heat flow, which is represented as Q, to a homogeneous solid object or material is directly proportional to its area, or to the area of the section at the right angles to the direction of heat flow. So what it means with the area of the section at right angles to the direction of heat flow, if this is the phase in which, or this is the material, the solid material in which heat is to pass through, the direction of heat transfer has to be perpendicular to this particular material or object. If it's not perpendicular to this particular material or object, then this particular law is not anymore applicable, because it's a requirement here that the area is to be at right angles to the direction of heat flow. And the formula also considers the temperature difference along the path of heat flow. So this is a differential equation because you see the derivative of the temperature with respect to location. This dx most of the time, class, refers to the thickness of the material. If the material is my hand, it refers to the thickness of my hand, because if this is the direction of heat flow, the distance covered during heat transfer starting from this side of my hand until here. So this dx is the thickness of my hand. Okay, the dt, or the change in temperature, will be the change in temperature or the difference in temperature of one phase over another, or against another, not over but against another. So the dt is the difference in temperature. Okay, so you have it negative ka dt over dx. So the reason why you have the negative sign in here, just in case for those who are wondering why you have the negative sign in here, would you know why we have the negative sign in here? Nga butangan naman di siya negative. Anyone who would know the reason behind why this is negative? Ka d capital T dx.
Kaya ang flow miss ang temperature from high to low.
Okay, thank you for that answer. So very good. This dt actually, if we use the premise of usually taking the difference of anything, it's always final minus initial. So true to what was shared, kung final temperature mo lubo kaysa sa initial temperature mo, because direction of heat flow is always from a high temperature section to a low temperature section. So this is your final temperature. So if you want the rate, the Q, it has to be positive at all times. So for it to be positive, you need to put a negative here. It's because, as mentioned, your dt will be negative because your final temperature, the temperature of this side, is less than the temperature of this side. Okay, so that explains the negative sign in here. Your K is a property of the material. It's a characteristic of that material. It's thermal conductivity. The higher it is, the greater the capacity of the material to transfer heat through it, or to let a certain amount of energy in the form of heat pass through it. Okay, because the greater the value of the K here, the greater is the value of the Q. So your T, the capital T that you see in here is the temperature X distance from the phase where the heat transfer started. So if this is the starting phase, what is this distance? This is X. Or this could be X sub 2 minus X sub 1. So the thickness of the material. Okay? So that's the temperature, the T is this T. The temperature X distance from this phase. If I'm talking about this as the starting phase of the material where heat is to pass through. Right. Now I will derive in a little while the formula from this DE. Actually, I'm sure majority would know of you would know how to get the formula from this particular equation, because this is just a simple case of separation of variables. Unless otherwise that the area that we're talking about in here is not constant. Like if it's a rectangular area, then whatever passes this face, the same amount of area is also passed through as heat is passing through this face. So constant siya. But there are materials which does not have uniform cross-sectional area. This particular cross-sectional area. So that would be a case wherein your A is a function of X already. Okay, so in that case, then we will have to separate variables dx with a, in that case, if a is a function of x. Okay, so that's our formula, and we have the sample problem in here, and we have the solution in here. Okay, so we can solve this problem in a little while. Let me just read the problem to you before I go to the page and Jamboard where I have already solved this morning to another class. So a copper plate that is 3 mm thick is sandwiched between stainless steel plates that are each 2 mm thick. So you have this copper plate here, the gold one, sandwiched between two stainless steel plates. This one is thicker than the two. So 3 cm for this, and this one is 2 mm. The left surface of the sandwich is held at 400. So this is the left side, and the right side is held at 100. The thermal conductivity of stainless steel is 17. And the thermal conductivity of water is copper is 373. So look at the discrepancy in the thermal conductivity of stainless steel and copper. So meaning copper has greater capacity for heat transfer than stainless steel. What are the temperatures at the left and the right surfaces of the copper plate? It's important when you solve a problem that you illustrate what the problem gives and what it requires. Since we have already the information, then I will just simply write on the required information in here. So in this case, we can label this side here. So it's asking for the temperature in this side and this side. So what are the temperatures at the left and right surfaces of the copper plate? So this is the left and this is the right. So since we do not know, you can assign any letter that you want. So in my case, I'd like to label it as T prime, and this part here is T double prime. This part here is 400 and this part here is 100. So one principle that we can use with heat transfer is this, and I'm sure this was discussed in your physics, that if you have a composite material, this one is a composite material because you have copper in between two stainless steel plates, the amount of heat that is being transferred from one material to the next would be equal. They should be equal. So what I mean is, if I will place this one as Q sub 1 and this one as Q sub 2, and this one is Q sub 3, these three should be equal. Your Q sub 1, Q sub 2, and Q sub 3 should be equal. Whatever amount of heat is transferred from this metal, stainless steel, is the same amount that will be passing through the copper plate, and then the same amount that will be passing through the stainless steel at the end here. Okay, on the right side of the copper plate. And our direction of heat transfer will be from the left to the right. Okay, as mentioned a while ago by your classmate, it should be from a higher temperature region or phase to a lower temperature region or phase. So this is our direction of heat transfer. So using this principle, we can get this T prime and T double prime using two equations with, of course, two unknowns. So this tells you in your algebra that you need to set up two equations because you have two unknowns. So one equation will not work. It will need another one. That way you can solve for the two unknowns. Okay, so I will share. Okay, I can't find the Jamboard. Wait, class, huh? Okay, new share. Okay. I need to clear everything. Okay, so as I have written in the screen showed to you a while ago, your Q, the amount of heat transferred, should be equal to all plates. Whether we're talking about the stainless steel plates that sandwich the copper plate, okay, which is represented here as Q3 in terms of the amount of heat transferred through it. So if we go back to the original DE, the original Fourier's law, written in mathematical form, if we separate variables, then we just need to cross multiply differential of x here. We can keep the Ka and the differential of t on the other side. Then place in the appropriate limits of integration. So x1 to x2, or that would be from the inner phase to the outer phase, or this would be the higher temperature to the lower temperature region. So in this case, T1 is higher than T2 because our transfer will be from higher temperature to lower temperature. So that's the purpose why you have the negative sign. So if you do the integrals, you will actually know that this is your formula. Q times the quantity x sub 2 minus x sub 1, where this x sub 2 minus x sub 1 is delta x, or the thickness of the material, and the right side is negative Ka. Of course, if you substitute the limits here after you're done integrating, will be T sub 2 minus T sub 1. Now, when you solve problems related to heat transfer where cross-sectional area is uniform, it does not vary with X, this is a formula that you can readily use. You need not start with the DE in here. So you can go straight to using this particular formula that I have boxed in red. Okay? So any questions so far with this particular formula taken from the original DE that was used to model heat transfer by conduction using Fourier's law? Do you understand this? Okay, so silence means yes, they say. So we will proceed. Now, if we will determine Q1, the amount of heat transferred in the stainless steel plate on the left side of the copper plate, if we substitute values on the Ka T sub 2 minus T sub 1 over thickness here, delta X, this would be it. So you have 15 A1 for the cross-sectional area of this face here. Then we have T prime minus 400. Why is the T prime minus 400? Because if we consider this plate, your final temperature is T prime, your initial temperature is 400. So that is why you have T prime minus 400. Your X sub 2 minus X sub, your X sub 1 minus X sub 2, or X sub 2 minus X sub 1, doesn't matter, is the thickness of the plate. So in the case of stainless steel, it's 2 mm thick. So we place here 2. You may wonder why I did not do any conversion, because your thermal conductivity class in here, as I have read a while ago, if you notice, is in Kelvin per, it's per meter, I think. Kelvin meter in the denominator. So let me just go back, so I can share to you. I may not give the correct. Okay, wait. Your K is watt per Kelvin per meter. So ang length dapat nga unit is in meter. So I did not convert anymore because later we'll be equating value. So what if I convert from one particular amount, I will do the same conversion to the other amount which I'm going to equate with it. So ang conversion ko mag-cancel lang. So amo na nga waay na ko nag-convert. So I simply wrote in the values because anyhow, as long as my units are uniform, I need not do any conversion. Okay? So balik ko to sa Jamboard ta. Okay. So if it's that of copper, the next thing is copper here. If it's that of copper, we now use the thermal conductivity of copper, which is 373. The cross-sectional area, let's say A2. And then we have the temperature difference. So it would be now T double prime minus T prime. And this time we will use a thickness of 3 mm. Okay, that's for Q3. What happens with Q2, this one here, Q2? It's the same as this one. The only difference is the temperature that appears here. So let me go to the next. So your Q2, we also have 17. We also have area here, same area. If you want, we can place here A3. It's actually the same area as this, as for the other stainless steel plate and that of copper. And take note of this one. It's 100 minus T double prime. This is 100. This is the temperature here minus T double prime. You have that. This time I divide by 2 because this is the thickness of our stainless steel plate. So I started with the principle that the amount of heat transferred from one metal will be equal through the composite metal. So you have Q1, Q2, and Q3 being equal. So in this case here, I've equated Q1 and Q2. So I canceled the 17, I canceled the 2s, I canceled the areas because we're talking of the same cross-sectional area in which we are to determine the amount of heat that is transferred through our composite material. So imagine my hand to be the composite material of copper in the middle and 2 stainless steel plates sandwiching it. So this is our remaining equation in red. If we will simplify, we'll get an equation of T double prime in terms of T prime, or it could be even T prime in terms of T double prime, doesn't matter, but this is your equation. The next thing is you have a choice actually. You can equate Q3 with Q2 or Q3 with Q1, doesn't matter because anyway, all 3 are equal. So in this case, your Q3 here was equated to Q1, okay, because we have T prime minus 400 here. So this must be Q1. And you have this after canceling the A's and the negatives. So you have this. And if we simplify, we have this one. Okay. And we can transfer, by the way, this is T double prime. And we can transfer, or we can, the proper term is cross multiply this expression here. Okay, so we have 248.67, this one here, 248. And the T double prime in here was changed to this one, 500 minus T prime. Okay, so I changed it by the way already. So this should be 500 minus T prime, because I changed it here already. This is your T double prime minus T prime. So if you simplify this, that would be 500 minus 2 T prime. And you have the right side to be T prime minus 400. So in here, you can get that T prime is equal to 250. And your T double prime is equal to 250 as well. That is if you take out 250 from this one. A T double prime is equal to 500 minus T prime. So this is our answer. So we got these two temperatures, the temperatures of the left and right faces, the left and right faces of our copper plate sandwiched by these two stainless steel plates using, so you use the fundamental principle, and this is the fundamental principle that you use. Take note, class, that this particular sample problem illustrates understanding of heat transfer discussed already in physics, and also illustrated the use of differential equation. So it's actually used, it's hitting two topics in one particular problem. Okay, so do you have any question with this one? Any question here? None? Okay, wait class ha.
Miss.
Yes.
Yan halin ng 500.
Ang 500. Wait, iyo ha. Di lang. I'll go back to my Jamboard first. Okay, share. Okay. Is the Jamboard still presented to you? Ara pa siya ang Jamboard. Makita
Yes,
nyo?
miss.
Sige. Dali lang. Dire siya naghalin. We equated Q1 and Q2. The amount of heat transferred to the stainless steel plates. Okay? And this is our resulting equation after all the cancellations that we did. This is our equation. If we simplify it further, it will be like this. So the 500 came from here. 100 transferred on the left side, that would be your 500 minus T prime, and that's your T double prime.
Okay, thank you, miss.
Okay. Question? Some more questions? We have 3 minutes more. You have questions? I can detect that some are not asking questions because you might because you might be thinking that Miss Ali will be thinking that's an elementary question. You ask a question whether it's elementary or non-elementary. Nothing is elementary or non-elementary if you want to learn. Rather than being silent there and me assuming that you get it. Later on, you apply what was discussed in here. So take note, I'm using the word apply. I'm not saying I'm going to give you the same problem, but you're going to use the same principle that was illustrated in this sample problem. So I'd like you to ask questions if there are questions that are still making your understanding incomplete. So no more questions. Everything is clear in here. Sige. So if there aren't any questions, okay, one here in the chat box. Miss, paano mabalaan if ma-T prime ka o T double prime? Very good question, Patricia. Very good question. Now, paano mabalaan, Miss, nga ma-T prime ka minus T double prime or T double prime minus T prime? You use the direction of heat flow. You use the direction of heat flows so that you will know how you're going to subtract the two. Isn't it that direction of heat transfer is from hot phase to a not so hot phase? So in this case, you have the 400 to 100. So this is your direction of heat transfer. The manner of subtracting, Patricia, is this is final. If this is your arrow, diri siya naghalin. This is initial, this is final. If we're thinking about this metal, but if we're thinking about copper, your final will be this, T double prime minus T prime. If you interchange the manner of subtraction, dako gid mo problema kay sala ginang answer nga gwa. So that is why I commended Patricia because the question is very relevant. So dapat final minus initial. Final minus initial. In the case of Q3, tanawan nyo si Q3, oh. Final. Oh, sorry. Is it Q1? Ari si Q1. Ari si Q1. Q1. Oh, hindi na si Q1. Q1 ari. Si Q1, ang final ya T prime, ang initial ya 400. Ano diya sa kay Q2? That should be 100 minus T double prime. Tanawon taanay ha. So si Q2, 100 minus T double prime. So it's always final minus initial. Okay, so another question on the chat box. Nagets ko na, Miss. Thank you. You're welcome. Sige. May question pa? Magsuli na ni siya gani, hindi na naamo inyo answer. Kaya tilain ang sa mahdaan, maglain lang sign, hindi na siya amo. Pag combine nyo na sa mga T primes kag T double primes, dito na mga problema. No, tsak to man to ginubra ko nga sa lancer ko, suli gali ang pag-subtract. It should be final minus initial. Actually, amo gina siya permit, tandaan nyo. Miski sa diin, miski chemistry, miski physics, final minus initial. Questions? Okay, ma-share ko screen ha, kaya ipakita ko ang canvas. I just borrow another minute because it's 2:31 already. What you have in Canvas are two sample problems. I chose this one because it's more complex. So I chose this one to discuss. This one is just direct substitution to the formula. So I leave this to you for you to read. Okay, basahon nyo na lang kay ma-substitute na malangta. What is new about this particular sample problem is you have to, of course, determine the area. Tiyak pus malag mag-determine sa cross-sectional area. It's the length times the width. So ari siya. Okay, so that's the area that was used in here. Okay, so I leave this to you as part of your reading assignments.